Have you ever stopped to think about what's really happening when you send an email, or stream a movie, or just, browse the web? There's this secret set of rules, an invisible blueprint that's running the entire show. And today, we're going to pull back that curtain and take a look at the TCP IP model. But first, to really get why we even need a blueprint like this, we have to start with a very common, very physical frustration. I guarantee you've experienced this one yourself. Oh, you know the one. That tangled mess of cables for every device you've owned since 2005. You've got one for an old iPhone, a completely different one for your tablet, another one for your e-reader, and none of them work with each other. It's just chaos. And this really gets to the heart of the matter. On one side, you have proprietary cables that create what we call vendor lock-in. Basically, you're stuck in one company's world. But on the other side, you have standards like USB-C, which create interoperability. Suddenly, everything can connect to everything else. It's the difference between being trapped and being free. Well, believe it or not, the early days of computer networking were exactly like that junk drawer. Different companies all built their own special networking rules. A computer from IBM couldn't talk to one from Dell. It was a total nightmare for data. So to fix this digital mess, the world needed a universal translator. It needed a common language that every single computer could speak. Basically, it needed a blueprint. And that blueprint is the TCP IP model. You can just think of it as the USB-C for the entire digital world. It's this open, standard set of rules that make sure a Cisco device can talk to a Google server, which can then talk to your Samsung phone. It's kind of the unsung hero that makes the global internet even possible. So, how does it work? Well, the model is brilliant. It breaks down the massive, complex job of global communication into 5 smaller, manageable layers. Everything starts at the top, at the application layer, where you, the user, create some data. And then it works its way down. Each layer has exactly one job to do, and that's it. This whole divide and conquer strategy is the secret to its success. All right, so now for the fun part. Let's actually follow a piece of your data on its incredible journey from your computer out into the wild internet, and we'll see exactly how these layers work together. It's a pretty wild ride. The main idea we need to wrap our heads around is called encapsulation. Just think of it like this. As your data travels down through the layers, each layer wraps it in a new digital envelope that has specific instructions for the trip. Let's say you're on your browser, and you click on a link to a hilarious cat video. That click, that request, that's our original piece of data. It's the letter we want to mail. Okay, so first stop, layer 4, the transport layer. It takes your cat video request and wraps it in something called a TCP header. This first envelope is all about reliability, making absolutely sure that the data arrives in the right order with no pieces missing. This whole package is now called a segment. Next, that whole segment gets passed down to layer 3, the network layer. And what does it do? It wraps it in another envelope, an IP header. This one contains the big, important addresses, the source and destination IP addresses. It's like writing the full global mailing address on the envelope. Now, we call it a packet. Then, it's on to layer 2, the data link layer. This layer adds one more envelope, but this one's different. It contains the local address, the MAC address, for the very next stop on the journey, like your home router. This final, fully wrapped package is called a frame. And at last, we hit the bottom. Layer 1, the physical layer. Here, that fully wrapped frame gets converted into raw bits, a stream of ones and zeros, and then zapped out as electrical signals on a wire, pulses of light in a fiber optic cable, or radio waves through the air. It's officially on its way. So our data is flying across the network. But how does it know where to go? Well, that's where the hardware comes in. Think of these devices as the traffic cops of the internet, and they work by reading the addresses on all those digital envelopes, and they're looking at 2 different kinds of addresses. A MAC address is a physical address. It's like your device's unique serial number, and it's used for local hop-to-hop delivery. An IP address, on the other hand, is a logical address. It's temporary, like your street address, and it's used to get your data across the entire globe. Your MAC address never changes, but you get a new IP address every time we join a new network. And here's how the actual hardware fits into our layers. You see, these devices operate at specific layers.
A dumb-old hub at layer 1 just repeats signals, but a switch at layer 2 is smarter. It actually reads those MAC addresses. And a router up at layer 3 is the smartest of all, reading IP addresses to make those big global routing decisions. So here's the key takeaway. A switch is like your local traffic director. It's sorting mail inside one office building, making sure data gets to the right computer on your local network. A router, though, is like the central post office for the entire city. It's the one that sends your mail to completely different networks, maybe thousands of miles away.
Okay, we have seen the journey and we've met the traffic cops. So, let's zoom all the way out and get back to the big picture. Why is this hidden blueprint so incredibly important? Well, when your cat video request finally arrives at the YouTube server, the whole process just happens in reverse. We call it de-encapsulation. Layer 2 strips off its envelope, then layer 3, then layer 4. It's like unwrapping a gift until finally your original request is revealed.
That's a pretty complex system, right? So what is the actual, tangible, real-world benefit of doing things this way? Why go through all this trouble?
The payoffs are absolutely massive. First, standardization and interoperability solve our charger drawer problem for good. No more vendor lock-in. Any device can talk to any other. And second, and this is huge for professionals, it gives engineers a logical map for troubleshooting. When your internet breaks, an engineer can ask, is it a layer 1 problem, like a bad cable, or a layer 3 problem with the router? It lets them pinpoint issues with amazing precision.
And that really is the power of the TCP IP model. It's this elegant, layered solution to an incredibly complex problem. It's the invisible, unspoken language that allows our entire modern connected world to exist. So the next time you click a link, you'll know the epic journey that simple request is about to take.